Alright, this video demonstrates how to use Muskingum method to draw downstream hydrograph from upstream hydrograph. The process of doing so is called flow routing. Since it is widely used in flood estimations, it is also referred to as flood routing. The downstream hydrograph would be different from the upstream hydrograph in a way that its peak would be lower and translated. The principle used to drive Muskingum method is quite simple. We know that the difference in the upstream inflow and the downstream outflow in a system is equal to the change in storage. If the inflow and outflow varies linearly with time, then we can use the average value as in here. To estimate the downstream outflow, it is necessary to get the storage function that links the input and output. Uh, so here comes the Muskingum method. The storage function in a river reach is linked with both inflow and outflow. S is equal to K times X into inflow plus 1 minus X into outflow, where K is the storage time constant for the reach and X is the weighting factor, which is around about zero point 0.2. From the equation, which we discussed earlier, we can express these terms in terms of the outflow, and the constants C0, C1 and C2 are given by zero point 0.5. C0 is given by 0.5 times the time interval minus K into X divided by D, where D is K minus Kx plus 0.5 times delta T. The important check here is that the sum of constant C0, C1 and C2 would be equal to 1. If it is important to note that if I0, if O1, the outflow, the first value of the outflow, the downstream outflow is not given, you can use the inflow value, the first inflow value as the first downstream outflow value in the numericals. Now we will go on to solve one numerical using the Muskingum method. So in this numerical it's given that the K is 3 hours, X, the weighting factor is 0.3, the time interval delta T is 3 hours, and we are supposed to draw a downstream hydrograph. The ordinates of upstream hydrograph are given. So the first step is to calculate D. The formula of D, as we know, K minus Kx plus 0.5 times time interval. So we'll get 3.6 C0, which is equal to 0.5 times the time interval, half the time interval minus Kx divided by D. C1 equals to half the time interval plus Kx divided by D, and C2 is equal to K minus Kx minus K delta T divided by D. Now we will use the check. The check is pretty simple. We will add the three coefficients and make sure that they are equal to 1. The sum is equal to 1. If the sum is not equal to 1, we will reduce the larger of the three values accordingly. Now we will go on to use the routing equation which we expressed in terms of the outflow. So the routing equation, the outflow, here since the outflow, the downstream outflow value is not given, the initial downstream outflow value is not given, So we will use the upstream inflow value, the first value, as the first value of downstream outflow. Okay, so we use 1 in this equation. Okay, we'll plug in this value here. We will calculate these outflow values by using this equation. We'll get a graph, and in the graph it can be seen the blue graph shows the upstream hydrograph, the red graph shows the downstream hydrograph. The peak of the downstream hydrograph, as discussed earlier, is slightly displaced rightward, and the peak is lower than that of the upstream hydrograph. So this is how we use the Muskingum method to get the downstream hydrograph from the upstream hydrograph.